So the basic idea of laminar flow patterning is that in the limit where the Reynolds number is low and the Peclet number is high, then the interfaces between flow streams are dictated only by the magnitude of the flow rates at the inlet. So I can have a device that looks like this. And I can have a device like this. And I can have a device like this. But as soon as I get far from a node, as soon as I'm looking at a straight part of the channel, if I'm putting in red at one of these inlets, and I'm putting blue in the other inlet, if I look at this part of the device, and I look at the relative widths of the red and blue aspects of the streams, this is dictated entirely by the inlet flow rates. And if I assume that the flow, if I assume that the device has a uniform depth, in fact, the width of these features is just given by a ratio of the flow rates. So for example, if I have a channel of width W, the width of the red stream in this case is given by W times Q1 over Q1 plus Q2. This is something that we expect to be true only far from the nodes. We expect it to be true only if the depth of this channel is uniform. And we expect it to be true only in these limits that we prescribed. Peclet number that's eliminating diffusion, and Reynolds number that is low and allowing everything to remain unidirectional and simple. And again, this conclusion is the same for this device as it is for this device as it is for this device. It doesn't matter that this is curvy. It doesn't matter that this was a thick inlet into a thin inlet. The only thing that's governing this is the magnitudes of these flow rates. And again, this means if I want to move things around, all I do is I change these flows. You can do this in real time, as long as the compliance of the system isn't too bad. Now, how might I use this? So I'd like to talk about two different relatively simple applications that illustrate how this very simple idea, right? I mean, we're taking the fluid mechanical equations and we're taking all of the interesting and hard parts about it, and what we're left with is these really simple algebraic relations. And we'll come back as the term goes by and we'll go back to doing some hard fluid mechanics stuff. But for the moment, as engineers, let's just take advantage of the fact that some of these problems are easy, right? If I can identify the location of a flow pattern by taking the ratio of two numbers, like that is super cool, and I can calculate that really fast as compared to calculating a complex flow. So let's talk about two applications. First, let's talk about cell positioning, specifically in the context of flow cytometry. And then let's talk about a technique called pinched flow fractionation. So how many people know what flow cytometry is? Some fraction, but not everyone. Well, metry just means we're measuring. Cyto refers to a cell. And so when we say flow cytometry, we're basically meaning that we're measuring properties of cells as they flow through a system. One of the simplest ways, and one of the most common ways that flow cytometers are used is by having cells and having these cells flow in a predefined pattern and then illuminating them with a laser and measuring a variety of different things. How much does the laser scatter in this direction? How much does the laser scatter in that direction? Does the laser excite fluorescence, etc.? And the details of what we might measure aren't a pressing concern right now, but this motivates a basic idea, which is that if I have a microfluidic device, let's make it F3 and let's if I have a microfluidic device with 3 inlets, this again is a top view. And let's suppose I'm going to put this microfluidic device in a housing that has a laser that's going to excite some region of the flow, and then it's going to be proximal to a number of different detectors, so a photomultiplier tube or something like that. And let's suppose that I set this up and I focus everything so that my laser shoots in and hits this spot right here. Right? And let's suppose that that laser focus is of a size that's approximately 1 micron in size. And let's suppose that I'm going to use that 1 micron size laser beam to look at cells, and let's say I'm looking at red blood cells. Those red blood cells are reasonably small. And let's say that this is my drawing of a red blood cell. And let's say that this is about 6 microns in size. Well, I presume it's obvious if this channel is, let's say, 50 microns wide, if all I do is I take some blood and I just shoot it through this channel, this isn't going to work very well at all. Every once in a while there'll be a red blood cell, and that red blood cell will go through my laser, and I'll get scattering, and I'll get fluorescence, and I'll get all sorts of stuff. But if this channel is 50 microns wide, actually most of the time I'm not going to measure this cell at all. It's just going to zip on by here or zip on by there. What I need to do is I need to make sure that that red blood cell always goes through this laser. Right, so let's suppose here is my blood, and then in these other channels I'm flowing in some salt water. Well, what would I do? How would I control these flow rates to make sure that every red blood cell goes through this laser? Right, I would have high flow rate of the salt water on both sides and a low flow rate of the blood. When I did that, my streamlines would look a little bit like this. Oops. It felt good, but not for very long. My streamlines will look like this, right? I've got blue salt water here, right? And then my blood is being squeezed into this small little stream. And that stream is precisely going through my laser beam, right? If someone goes up to my system and they kick it on the side and they misalign the laser, and now my laser moves from here to here, what could I do to fix this other than fixing my laser? Well, all I have to do is I increase this flow rate, decrease that flow rate. I can move my blood back and forth. And again, this comes from simple geometry, simple arguments about the momentum transport, simple arguments about the diffusion. It means, again, I'm using algebraic relations to control things. So this actually is a homework problem. So the third homework has a system where you need to solve a set of matrix equations to come up with a relation between the different pressures in the system and the flows. And then I believe I postulate something that's akin to what I just described, a flow cytometer where the laser got misaligned. And what you'll see is that, going from one design to the other design is super simple. You just change one parameter, invert the matrix again, and you're done. Cool.
Wouldn't it be a problem if I wanted the cell to be under the laser for say 1 second or so? Because the smaller you make the blood stream, the faster it's going to go. So the cell is just going to zip through the laser spot and.
So the question was, how do the sizes of these relate to the velocities? And one thing to keep in mind is that this is not a case where the streamlines are converging because of acceleration, right? We know in general that when we accelerate a flow, the streamlines get closer together. And so the converging of these streamlines can be associated with an acceleration, right? So that acceleration is happening, right? Because by definition it has to. In an incompressible flow, if the streamlines are converging, it's accelerating. But that acceleration is happening here, right? So if my flow rate here is big, and my flow rate here, by definition, has to be small, I've got this blood creeping through super, super slowly, and then it accelerates in this region so that the velocities of all three of these components are the same. Similarly, if you, and I didn't draw this very carefully, if you assume that these were of the same size, the salt water would be decelerating because it's expanding out. So there is acceleration and deceleration. It's all happening here at the node. And in fact, all the details of this streamline, all the interesting stuff happens at the node. But we want to look at it downstream, at which point the velocity is everywhere. The z-averaged velocity, the average in this direction, is uniform everywhere. And in fact, that assumption is what led us to say that this location is W times Q1 over Q1 plus Q2. So in fact, the velocity of this blood cell is given by the mean velocity of this flow. And that's the only thing it's given by. So compressing it more and more just means basically that this upstream blood is flowing that much slower. But it doesn't change the velocity of the blood cell at this point.
The velocity of the cell at that point would be the velocity of the salt.
Correct. Everything has the same z-averaged velocity. Right, so we're using basically a 2D analysis. Actually, as I'm drawing it, I'm implicitly using a Healy-Shaw analysis, where I am assuming that the z-averaged, all of the dependence in the z direction is independent of the dependence in x and y direction. So I'm assuming it's a separable problem. And I'm averaging that out and basically ignoring it. And we'll talk about the details of that sort of analysis later. But for the moment, I'm saying, well, if the average velocity is the same everywhere, then the mass flow relates directly to the location of the interfaces. So I don't remember what your question was or if I answered it.
No,
it's always no.
basically, the point is, with respect to the velocity of the blood at the inlet,
Correct.
the velocity of the cell takes the velocity of salt.
That's correct. Yeah, Helen.
So I was just wondering, what exactly is the effect of having a non-Newtonian fluid flowing in this geometry? Because I know that blood itself is not Newtonian.
Yeah, so the question is, what's the effect of a non-Newtonian fluid, especially given that blood is known to be non-Newtonian? Yeah, so blood's complicated because it's a Bingham plastic in the sense that technically speaking, as you go down to a really, really low shear rate, it acts like a solid. Above a specific shear rate, it starts to act now like a shear thinning fluid. So it's often categorized as a caisson fluid. The key question in terms of how that affects things, right? So McCool asked about the role of the viscosity in non-Newtonian fluid in a Couette flow, right? So in a Couette flow, it doesn't make a difference. In a Poiseuille flow or something that's approximating a Hagen-Poiseuille flow like this, if you have a fluid that, for example, is shear thinning, you get lots of gradient at the edge and not very much in the middle. So it basically takes the parabolic profile and straightens it out to make it look more like a uniform profile everywhere. The key thing with blood, blood's really a colloidal suspension, and its most dramatic non-Newtonian fluids come from the suspension itself not from the fact that the serum is technically shear thinning, but that actually isn't a big deal. So in an application like this, you're really diluting the blood a ton. When you dilute the blood a ton, it's perfectly fine to assume that all of this is Newtonian. If, though, we took a fluid that was strongly non-Newtonian, like we took a polymer solution that was strongly non-Newtonian, and we tried to do this sort of analysis, what you would find is that out here, you'd get small perturbations because of the changes in viscosity. The fact that it was non-Newtonian, especially if it's viscoelastic, would make things be really interesting here where there's a lot of change. Another thing you would note here is this center flow is inherently an elongational flow. So for a polymer solution, that elongation will tend to elongate the polymers, and it will tend to reduce the viscosity locally, because you basically take a jumbled up polymer that can get tangled with itself, and you stretch it all out in one direction, and you make it so that the polymers will slide along each other pretty well. Other questions or comments? Okay. So, two basic ideas. Remember, simplest analysis ever. We're just assuming that the sizes of these things are proportional to the flow rates, but it gives us an immediate idea of how we can do flow cytometry. Let me talk about another example, what's called pinched flow fractionation. So pinched flow fractionation is based on the idea that the pattern of this flow, the location of interfaces, the location of streamlines, can really be expanded or contracted arbitrarily. So if I have two flows that go into a narrow channel, they'll be separated by an amount that's defined by the fractional value of the flow rates. If I have that same flow go into a thick channel, then things will be separated by fractional values of that thick channel. But it all ends up basically the same. So now let's take this same sort of geometry. In this case, I'm going to have two inlets. And let's again add some red and some blue. Now, if I have a flow rate of blue that's Q2, a flow rate of red that's Q1, I'll get some sort of thickness of this flow. This thickness of this flow again is dictated by Q1 relative to Q2. So if I again define this as being equal to W, this thickness here will be given by W times Q1 over Q1 plus Q2. Now if I send this flow into a big thick channel, and again I look far out here, how will the distribution of red and blue look different out here as compared to on the left? If I say that this has a thickness now that I'll call W sub 2. Yeah, Nikolai. Well, we basically increased the length scale. So there's a chance that in some contexts we could increase the Reynolds number. It turns out usually we don't increase the Reynolds number by doing this. So we've increased the Peclet number. So we actually haven't given this flow we haven't made the diffusion problem any easier. In fact, all we've done is we've made the length scales bigger. So inherently, we still expect this flow to have effectively no diffusion. But if I want to locate the interface between red and blue in this case, how thick is the red flow?
The fraction will still be the same, just multiplied by different factor of W2.
Yeah, the fraction's the same, but now just W2 is bigger. Right? So I expect that this flow is basically going to look like this. this thickness here is now just W2 times Q1 over Q1 plus Q2. So nothing has changed topologically about this flow. I basically just expanded it out. Took up the Q1 over Q1 plus 2 fraction here. It's taking up the Q1 over Q1 plus 2 fraction here. But undeniably, the physical dimensions have increased. I've basically just taken this shape and I've expanded it out. Now, why might this be important? Well, let's consider that I take this same flow, and now rather than mixing red dye and blue dye, now I want to mix together a set of particles with a flow that has no particles. So we're going to assume that this blue flow has no particles, and we're going to assume that this red flow has some small particles and some big particles. And everything in between. Now, as I've drawn this flow right now, the location of these particles is basically randomly distributed in this red flow. And if this width continues to be big in this constriction, my yellow particles will continue to be randomly distributed in this red flow. And if I look all the way down here, my yellow particles will be randomly distributed in the red flow. So nothing interesting has happened. Right? I've got some particles in my red flow. They're randomly distributed here, they're randomly distributed here, and they're randomly distributed here. What could I do, though, to change the fact that the yellow particles are randomly distributed? Using the techniques we've talked about today, right, which is basically changing the magnitudes of the flows. What's that? Well, definitely shear-induced particle migration would have the potential to do a number of things to this distribution. But that's fancier than I have in mind. I have something very simplistic. Yeah?
If you choke the red flow at the narrow part,
Mm-hmm.
it will line up.
Yeah, so let's suppose I'm going to crank up the blue Q2 and I'm going to turn down the red Q1. Right? So what happens when I do that? This interface moves toward the wall. Right? So this interface moves toward the wall. This interface moves toward the wall. And let's suppose when I squish this, I squish this so much that now this red flow is small as compared to the characteristic sizes of the radii or diameters of the particles. Right? So I crank up Q2. I kind of make this blue thing take over more. Right? And now, because I'm smashing this up so much, these particles all line up against the wall. Now when I look at these particles downstream, what is different in this case as compared to the case before? Pardon? They'll be ordered in what way? You all became inspired all at the same instant. So they're going to be ordered. In what way will they be ordered? My smaller ones are closer to the wall, which means when they come out here, they're going to be closer to the wall, right? So I expect my little particles are going to flow down this path. My big particles, I tried to smash them up against the wall, but I couldn't smash them completely because there's a steric hindrance. Like there's only so how much you can smash it up. This is actually on a different streamline. It's on a streamline that's farther from this top, right? So these big particles are going to come out on a path that looks like this. Okay. So this technique can be used to fractionate particles into different sizes. All you have to do to make this happen is you have to take your flow with particles, smash it up against the wall enough so that the distance these particles are from the wall is dictated by their size rather than by the flow. Then when you expand this out, this expansion is just a linear expansion of the location of these particles. And when you do this linear expansion, now the locations of these different sized particles is transduced, or the different size of these particles is transduced to a different y location. Right? So now I could take this device And in principle, I could say, all right, I'm going to have one outlet here for the small particles, and I'm going to have another outlet here for the medium particles, and another outlet here for the big particles, and on and on. So you'll have a homework problem where I'll have you take this basic geometric idea and work through what are the different design parameters that can lead to your taking a particle here and knowing how it's going to come out. What are the uncertainties associated with that? What happens if you have a pump that's not perfect and you don't know exactly how much the flow is, or the flow varies plus or minus 5%? What advantages do you get when you smash this a lot, or if you smash it not very much? Right, you basically find that the separation between these particles is big if the ratio between this and this is big, which makes you want to make this constriction really, really small. But if you make it too small, then the whole thing clogs, and on and on and on. And this can be made to be a relatively sophisticated separation of particles. If you want to, for example, separate red blood cells from white blood cells with this sort of approach, no problem. And again, it all comes from just this basic laminar flow patterning idea that says that in simple geometries with simple flows, the location of these streamlines is dictated by the relative flow rates, and then I can transform that any way I want. Comments? Questions?